Thermodynamics Chapter 3, Lecture 1. First thing, let's define what's known as a pure substance. A pure substance is a substance that has a fixed chemical composition throughout. Air is a mixture of several gases, but for our purposes, it's considered to be a pure substance. So two examples are nitrogen and air, gaseous air. These are both considered to be a pure substance. So a mixture of liquid and gaseous water is a pure substance because it has the same chemical composition. But a mixture of liquid and gaseous air is not considered a pure substance. A pure substance can have different phases. For example, we have the solid phase, the liquid phase, and the gaseous phase. The key difference is how close the atoms are bound together. In a solid phase, molecules are at relatively fixed positions, kind of like structures of a building. A liquid phase, the groups of molecules move around about each other. In a gaseous phase, the molecules simply move around at random at wide distances from each other. One concept that we need to understand is that in order to build a device that we can get useful work out of, we're going to have a fluid moving through it that's going to change phase. So typically in a turbine that we're converting liquid water into steam, that steam moves across the turbine blades to turn the turbine blades, to turn a shaft, to make electricity, or drive a propeller to push a ship through the water, for example. In the automobile engine, we take in liquid gas and burn that gas to convert it to vapor phase. That vapor phase, then we hit a spark and ignite the spark, cause the engine of the automobile to turn over. So we need to understand how pure substances change phase and the different phases of pure substances. So we're going to define several key terms. For one is what's known as a compressed liquid. That's what's known as a subcooled liquid is another name for it. This is a substance that is not about to vaporize. Its temperature or pressure are well below the saturation temperature or pressure. The next term is saturated liquid. This is a liquid that is right at the temperature to turn the liquid into vapor, but it's all still liquid. We refer to that as what's known as a saturated liquid. So let's take a pure substance in state 1. It's at a pressure of 1 atmosphere and 20 degrees C. And let's imagine this is water. Well, we know that water vaporizes at 100 degrees C. So this at standard atmospheric pressure. So this pure substance in state 1 is well below the boiling point for water. So we refer to this as a compressed liquid. Let's apply heat to this state 1, heat it up until we're at 1 atmosphere at 100 degrees C. Well, now we're exactly at the boiling point for water. So, but it's all still, in this case, it's all still liquid, but it's at the point of turning from liquid to vapor. So right at that point before it turns to vapor, we refer to that as what's known as a saturated liquid. Water exists as a liquid, but it's ready to vaporize. If we apply any more heat to it, we're going to start converting the liquid into vapor. Saturated vapor, a vapor that is about to condense. So this is a vapor. It's a gaseous phase. It's all vapor, but we're at 100 degrees C. So if we cool it down any more, it will begin to turn the vapor into liquid. Saturated liquid vapor mixture. This is a state in which liquid and vapor exist in equilibrium. And the last state is known as a superheated vapor. This is a vapor that's well above the boiling point for that particular pure substance. So for water, this would be maybe, let's take water vapor at 200 degrees C. Well, that's well beyond the boiling point of 100 degrees C. So that vapor is all vapor, and it's well above the boiling point. So here's, we keep heating up the water. We reach 100 degrees C. We keep applying heat, and so some of the liquid begins to turn into vapor. So at this point, we have both saturated vapor and saturated liquid together. We apply even more heat, and as we do that, more of the liquid turns into vapor. We'll reach a point where all of the liquid has been turned into vapor. We're still at 100 degree heat, 100 degrees C, because this temperature is not going to change until all the liquid's turned into vapor. All the heat we apply, that's all it's doing is turning the liquid into vapor. So when it's all turned into vapor, that's what's known as a saturated vapor. If we apply any more heat, then the temperature starts to rise. The temperature only starts to rise once it's all vapor and we're at 100, and we would be at the 100 degrees C. Then we can apply more heat, bring it up above 100 degrees C, it becomes a superheated vapor. So it's very important to understand these different terms. We'll use these terms a lot, and so it's important for you to know what the difference between a saturated liquid vapor mixture, saturated vapor, and a superheated vapor. So if you plot those 5 phases on a diagram, if you plot temperature on the vertical axis and you plot specific volume on the x-axis. Now, specific volume is something you're probably not used to dealing with, but it's the inverse of density. So density is mass over volume. Specific volume, which is denoted by a small v, is volume over mass. And the reason we do this is because we want to take the mass out of the equation. We want to graph this graph per unit mass. That way we can have one chart for example, for water. We don't have to really worry about what the mass is, because for this curve is going to look the same no matter how much mass we have of water. It's going to look the same. The same values are going to be there on the horizontal axis. So we started at 1, which we were a subcooled liquid, compressed liquid. We heated it up to phase 2, and then during phase 2 to 3, remember at 2 it's still all liquid, but it's at 100 degrees C. We add more heat. We start converting the more of the liquid into vapor, and in state 3, it's a mixture. It's a saturated liquid vapor mixture. We add more heat to get to point 4, and at point 4, it's all vapor at 100 degrees C. We add more heat, and then only then does the temperature start rising. So from 4 to 5, we become what's known as superheated vapor. So remember this chart. I mean, it's very critical that we actually that you actually understand where each of these points are. So at point 3, you have to know exactly what you're dealing with there. Same at point 5. The temperature at which water starts boiling depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. So we know water boils at 100 degrees C at 1 atmospheric pressure in the metric system. In the English system, it's 212 degrees Fahrenheit at 1 atmospheric pressure. The saturation temperature, denoted as Tsat, is the temperature at which a pure substance changes phase at a given pressure. Saturation pressure is the pressure at which a pure substance changes phase at a given temperature. So you can plot these on a curve, the saturation pressure versus saturation temperature, and you can see what the curve looks like. The liquid vapor saturation curve in numerical values is shown in the table 3.1. So using this table, you can figure out exactly if you're at 100 degrees C, for example, you can run over and you can figure out what the pressure is. Saturation pressure for that, for different temperatures. So if you graph each of these on a curve, each of these values are going on. So we're graphing temperature versus specific volume. This is what's known as a TV graph, TV diagram. So if you graph this at different pressures, you can see they all have similar kind of shape. So this first graph is at 0.01 million pascals. You can see the points are the same. So here's your point where it's a saturated liquid. Here's a point which is a saturated vapor. You go up in pressure, you can see the curve shifts a little bit, but it maintains its basic shape. Here's 1 million pascals. Uh, you keep moving up in pressure, you notice this part where it's a liquid vapor mixture gets shorter and shorter until you reach up a point here, known as the critical point, where it goes from liquid to vapor automatically. It doesn't. There's no liquid vapor mixture phase. That's the critical point, and that occurs at 373.95 degrees C at a volume of 0.003106. So if you take these curves and you hook up the or you imagine connecting dots for the uh, saturated liquid line and saturated vapor line. So here you would just connect the dots all the way up. You would get this kind of curve, this kind of dome shape. So this dome shape is very useful because anything below the inside the dome is the saturated liquid vapor region. The boundaries on the left are the saturated liquid line up to the critical point. Then after the critical point, it's the saturated vapor line. Anything to the right of the saturated vapor line is the superheated vapor region. Anything to the left of the saturated liquid line is the compressed liquid region. So this critical point again is defined as the point at which saturated liquid and saturated vapor states are identical. At supercritical pressures, if you're greater than that critical pressure, there's no distinct phase change. You go right from liquid to boiling. There's no liquid vapor combination kind of region there. You can also have what's known as a pressure versus specific volume curve. In that case, we would graph pressure on the vertical axis versus specific volume on the horizontal axis. The dome-shaped region looks exactly the same. You have the critical point at the top. You still have the saturated liquid line and the saturated vapor line. And the three regions are the same. You have the compressed liquid region. Under the dome is the saturated liquid vapor region. And to the right is the superheated vapor region. The difference is the curves go down, across, and then down again. So, and these curves are at specific temperatures. So this is the constant temperature lines. Whereas on the other curves, remember that if we were graphing temperature versus specific volume, the curves go up here, across, and then up like that. In this case, they're exactly the other. They go exactly the other way. So just keep in mind that temperature versus specific volume, the curves go up, across, and then up, and then on pressure they go down, across, and then down.